Okay, for number 1, they want us to evaluate this function. So we will go through and do some substitutions. And so for the first part, we're going to plug in a 9. And when we do that, f at 9 is going to be equal to 9 minus 2 over 2 times 9, which is 18, plus 3. So we're going to get 7 over 21, which will reduce to 1/3. Number 2, we're going to substitute in x minus 1, and so f at x minus 1 equals, and in the numerator we're going to have x minus 1 minus 2 over 2 times x minus 1 plus 3. We do need to work out some of the algebra, and this would be a -1 minus 2, so minus 3 over, and here we're going to have 2x minus 2 plus 3, so that's going to be 2x plus 1, and we can't reduce any of that just because there's no GCF. Looking at number 3, we're going to substitute in here 2x minus 1 into this function. So g at 2x minus 1 is equal to 3 times 2x minus 1 minus 2x minus 1 all squared. We do need to simplify this. We're going to have 6x minus 3 minus, and now we need to FOIL this out, so that's where we would say, okay, we've got another 2x minus 1, and we've got our first, outer, inner, and last. Our first term would be 4x squared. Our outer term would be negative 2x, the inner term negative 2x, and the last term plus 1. So when we put together our like terms, we have 4x squared minus 4x and then plus 1. And now we can go ahead and distribute our negative and do some like term collecting, or we can go ahead and just distribute the negative to see what we have. That's negative 4x squared plus 4x minus 1. And then if we put together what we can, we should have negative 4x squared plus 10x minus 4. All right, moving on to our next problem. Again, we're going to substitute in a negative 3x here. So g at negative 3x is going to be 3 times negative 3x minus negative 3x all squared. So g at negative 3x is going to be negative 9x minus 9x squared. And we can't put those together, so that would be your final answer. Okay, for question 5, again we have a piecewise function, and when we're substituting in -7, you don't substitute into both parts. You need to see where is -7 in terms of these inequalities, and -7 is less than -3. So when we evaluate h at -7, we're going to substitute into the top part of the piecewise function. And so we're going to have the absolute value of 28 plus 7, and so we're going to end up with a positive 35. Okay, looking at the next part, h at -3, notice that that -3 would fall into this bottom portion because it says greater than or equal to. So when I substitute in here, I have h at -3 equals, and I have a negative from the actual problem itself. -3 is being substituted in, plus 2 times -3 all squared. So here we have the negative from the problem, and then we have a -27 from the cube, plus 2 times 9. And so we're going to have 27 plus 18, and so we're going to get 45. Okay, in the next part of the review, it's very important for us to be able to identify and sketch our parent functions. So when we go through here, notice you're just told that you need to write or sketch a linear function. And so first thing, we need to identify that as f of x equals x. And then whenever we sketch this, it is just your linear function through the origin. And so there's what that function should look like. Absolute value, that's going to be f at x equals the absolute value of x. And that should be a v with the vertex sitting here at the origin. With your quadratic, that's going to be your x squared, so f of x equals x squared. And again, you're going to do your U shape here. And so now we're to our cubic. Okay, the next one is cubic, so that means that we're going to have f of x equals x cubed. And for our cubic function, keep in mind the shape of that. Our next problem that we have would be the square root function, and that's going to be part of the inverse of a parabola or quadratic. And so that's going to be f of x equals the square root of x. The next one, cube root. Again, our function f of x equals the cube root of x. And that's going to be your cubic function on its side. So it's going to look something like this. Okay. And now let's look at our reciprocal. And what's important with the reciprocal function is that you remember that you're going to have your asymptotes here for x equals 0 and also your y equals 0. You have those asymptotes there, and just your general shape. The graph is going to be bent when it goes toward the x or y axis. And our reciprocal function, f of x equals 1 over x. And then finally, the greatest integer function, the notation of that is kind of strange. And for your greatest integer function, f of x equals, you're going to have the weird brackets and your x. And then do keep in mind that it is the integer closest but not greater. So you're going to have all of these open circles out through here. And this was also the function that we said could also be known as a step function. So again, we have all of these going along up through here. And we'll draw in one more just for grins. Number 15 says that if we have a quadratic parent function is reflected in the y-axis, vertically compressed by a factor of 1/2, write an equation to represent the new function. So the quadratic parent function is x squared. So we're going to have f of x equals, and notice we are reflected in the y-axis, so our negative needs to be on the inside of the function. And vertically compressed, which is going to be on the outside, it's exactly by the factor that it says. So we have a 1/2 there. All right, number 16, we have a cube root parent function is horizontally stretched by a factor of 4. So keep in mind here with the horizontal stretch, it is not by the factor of 4, but would have been 1/4 on the inside of the function. Then we are translated right 5 units, so we're going to subtract 5 and then 3 units up. So our new function, f of x equals, and we're going to have our cube root, so it's the cube root parent function, and we are horizontally stretched by 4, which is going to be a 1/4 on the inside of the function, times, and translated right, that's going to be x minus 5. And then we're going to have this translated up 3 units. So we're going to have plus 3. All right, number 17, the absolute value parent function has transformations applied such that it creates an absolute maximum. So there's one of those major points that we've talked about at -2, 7. So a good way would be to sketch this. Notice it says at -2, +7. So we go back to up 7. And if that's a max point, then that means that our function has been flipped upside down. So that tells us quite a bit about what we need to do with our new equation. We are flipped upside down, so we have a negative absolute value. And if we translated 2 units left, we need a +2 on the inside, and then up 7 units, so +7 on the outside. All right, number 18. Let's see. It looks like this did not copy over good. On this, you should have, I would believe, is the greatest integer function right here. Okay, and so now let's see what we've got. We have a certain function is vertically stretched by a factor of 2, horizontally compressed by 1/4, and then translated down 6 units. And the new function is what we're given, and we need to do the original function. So we need to go back and undo a lot of these things. So my original function would be, and so let's start here, vertically stretched by a factor of 2. So that means on the outside I multiplied something by 2. So I can undo that by dividing, and that's going to give me a 3 for the outside. Okay, now let's go ahead and look on the inside, horizontally compressed by 1/4. So we know for a horizontal it's the opposite, so we know we've multiplied by 4 on the inside. So to undo that, I need to divide 8 by 4. That's going to give me a 2. And then on the outside, we were translated down 6. So if I moved down 6 and ended up at -2, I need to add 6 to move it back. And so that's going to give me a +4. All right, so for number 19, we need to describe all the transformations from the parent function given below. So when we go through and describe these, let's start on the outside here. So the first thing I notice is that we are reflected in the x-axis. Okay, and we also have a 3 on the outside, so we have a vertical stretch by 3. On the inside, we have a horizontal stretch. It is always the opposite of what you would think. So there's a horizontal stretch, and that's going to be by the reciprocal, so by 2. And then we're going to be moved up up 7. All right, so looking over at number 20, we're going to go through that same process. So again, starting on the outside portion, we have our 2/3, so that means that we have a vertical, and that 2/3 is less than 1, so it's going to be a compression by 2/3, by what it says exactly. The negative on the inside, so we are reflected over the y-axis, is the negative on the inside. We are also moved to the right 5, and we are also moving up 2. Okay, for number 21, we need to sketch this and find certain things about it. And so the first thing I'm going to notice here, this is our reciprocal function. So the parent function here was 1/x, so we know the general shape of it. We also know that this has been moved to the right 4, And so right away we see that that denominator, moving that right 4 is going to move an asymptote over from 0, 0 over here. And it is important to have that asymptote noted. And if we want to find out where we cross the x and y axis, remember that we did have either our graphing calculators, or we could go through and do some zero substitutions. So for the first part, I'm going to let my y value be 0. So that means I'm finding the x-intercept. And so I'm going to have 0 equals x minus, or 3 over x minus 4 minus 1. I'm going to add 1 over. So I have 1 equals 3 over x minus 4. I'm going to multiply my x minus 4 over. And so we see that we're going to get an intercept of 7. So my x-intercept is going to be at 7. So 1, 2, 3, 4, 5, 6, 7. So I know this graph is going to cross right there. And so now let's go look at our other intercept. And so for that one, we're going to let x be 0. And if we do that, then we have f of x, or y, is going to be equal to 3 over negative 4 minus 1. So f of x is going to be negative 1 3/4. So that's going to be my y-intercept. So negative 1 3/4. So we're almost down here at 2. Right, and we've also moved down 1, so that also means that that horizontal asymptote has been slid down here to negative 1. So we also have that asymptote going for us. And so now we can do our general sketch of this. So here we're going to run right along that asymptote and then take a nosedive. And then up here, same thing. We're going to run along those asymptotes and then take a nosedive there. All right, so now let's fill in our information. So over here for our domain, we're going to have all real numbers except, and that's going to be where that asymptote was, that vertical asymptote. So that's going to be except 4. Our range is going to be all real numbers except for, again, an asymptote, and that was at y equals negative 1. Our intercepts that we found, the x-intercept was at 7, 0, and the y-intercept was at 0, negative 1 3/4. As far as extrema, we don't have a maximum or minimum value through there. Increasing, this function is not increasing, but it is decreasing from negative infinity up until our asymptote at 4, and then on the other side of 4 to infinity. And our end behaviors, as x approaches positive infinity, f of x for this one is approaching negative 1. As x approaches negative infinity, f of x again on that other side is approaching negative 1. Okay, for our next problem, we have a quadratic parent function. So we know we're going to have a general U shape. With the 2 on the outside, we know we have a vertical stretch of 2. We have been moved to the right 3, and then we've been moved down 4. So we know a little bit about this. So a vertical stretch, that means we're stretching this vertically, so it's probably a little skinnier. So we can do a quick sketch of this. We've moved to the right 3, and then we've moved down 4. Okay, and so we know we've got kind of a skinnier stretch here. Let's see, we can go through and do some estimates here. Kind of a good sketch. All right, and also, let's see if we can't find our x and y intercepts. So for the first part, we're going to let y be 0. And so we're going to have 2 times x minus 3 all squared plus 4, or minus 4, sorry. And we're going to add our 4 over. 2 times x minus 3 all squared. Divide by 2. And it looks like we're going to get some weird funky decimal mess. We're going to do the square root. And don't forget we need plus or minus 2. And that's going to be equals x minus 3. So when we add our 3 over, we have 3 plus or minus root 2 equals x. So that's going to be like 3 plus and minus 1 point stuff. So however you want to do that, you can leave it in exact form. That's perfectly okay. Now for the y-intercept, we're going to let x be 0. So then that's going to be f of x equals 2 times 0 minus 3 all squared minus 4. So f of x equals 2 times 9, so that's going to be 18 minus 4. So our y-intercept here is going to be 14. So when we come over here for our x-intercepts, we know that that's going to be 3 plus or minus the square root of 2, or you can type it in and get some kind of decimal mess. And then your y-intercept, we found that to be 14. Now for our domain with quadratics, your domain is all real numbers. Your range, notice we need to start way down here at that vertex. And so here our range is going to be from way down there at negative, I believe it was -4, all the way through positive infinity. And this one would have an extrema. The extrema, we're going to have an absolute min because this is the lowest value over the entire domain. So we have an absolute min at, and that point was 3, -4. Our increasing interval, well, that's going to be, and you're always looking at your x, so you're increasing from 3 to infinity. And we are decreasing from negative infinity. Oh, don't need brackets around the infinity. Sorry, guys. Parentheses, negative infinity to 3 bracket. All right. And so now our end behaviors. This is what's going on at the end of the function. Well, as x approaches negative infinity, that side of our function is approaching positive infinity. And the same on the other side. With your quadratics, your end behavior, they're both probably going the same direction, or you don't have a quadratic function. Okay, our next function is our cube root function, and looking at this, we see that we have a vertical stretch of 2. We've been moved to the left 4 and up 3. All right, so we do need to move this normally, our cube root function, and this one's kind of hard to draw. There's the original, and so I'm going to focus on this point right here. That's the one I'm going to pick up and move. So if I move this, I'm going to go, let's see, left 4, and then up 3, and I'm going to drop it. So right there is where that point is being transformed. So it's going to look something like this. And so now we can go back and hopefully connect it. Right? And so looking at some of our points that we need to find, if we go through here finding those intercepts, again, if we let f of x be 0, and we have 2 times the cube root of x plus 4 and then plus 3. So I'm going to subtract 3 over. So 2 times the cube root of x plus 4. Divide by 2. So definitely going to get some fraction mess here. we need to cube both sides. So I'm going to have negative 27 over 8 equals x plus 4. And then when I subtract 4 over, I'm going to end up, let's see, we're going to have negative 27 over 8 minus 4. Well, 4 is going to be 32 over 8, and that's going to equal x. And so that looks like we're going to end up with a negative 59 over 8. That equals x. So that's going to be a little bit more than 7, or you can put your decimal mess at 7 point stuff. Now let's go through and find your y-intercept. So I'm going to have 2 times the cube root of 0 plus 4, and then plus 3. And that's about all we can do with that. And again, that's going to be some small decimal mess. All right, so over here for our x-intercept, we've got negative 59 over 8, comma 0. And then for your y-intercept, that exact form, 0, comma 2 times the cube root of 4. And then plus 3. All right, or you can type all of that in your calculators and get your decimal stuff. Your domain is going to be all real numbers. Your range is all real numbers. You don't have any extrema. And this function is an increasing function, and it is increasing from negative infinity to infinity. You don't have any decreasing intervals, and your end behavior as x approaches infinity, f of x is also approaching infinity. As x approaches negative infinity, f of x is also approaching negative infinity. Our next problems, they want us to identify the domain, the range, and state the location and type of our discontinuities. So for our domain, we're going from far left to far right, and it looks like we've got a discontinuous domain around in this area here. So I'm looking on still, and it looks like we might have an asymptote here at 1, 2, 3, 4, 5. So our domain looks like it's all real numbers except they're at 1 to negative 3, and also over there at 5. Our range is far from the bottom to the top. That looks like everything's accounted for, so that's going to be all real numbers. And our discontinuities, it looks like at x equals negative 3, and over here at 1, 2, x equals 2, you have a jump discontinuity. And then at x equals 5, you have an infinite or a vertical asymptote, either one. Right, number 25, as far as our domain here, as far left to as far right, even though we have open circles, it looks like everything is accounted for, so all real numbers. And then, let's see, for our range, looking at the range, I think from negative infinity all the way up to here, 2, 3, 4, 5, 6, and that's not included. So from negative infinity, it looks like, all the way up to 6 not included would be your range. And it looks like we have 2 jump discontinuities. We have at x equals 1, 2. So at x equals negative 2 and x equals 1, it looks like we have a jump discontinuity. Okay, for number 26, we are going to be graphing our piecewise function. And just like we did before, it's a good idea to go ahead and mark off our borders. So I'm going to mark off negative 4. 1, 2, 3, 4. So I know right here is going to be a place where I have a border. And then over at positive 1 is the other place. So we can see where we're divided up, definitely, into our 3 different parts. And for our first part here, again, you always start with this border point. You're going to substitute in right over here. And so for the first part, we're going to have negative 3 over 2 times negative 4, and then minus 6. And you can treat that negative 4 over 1. Negative times a negative is positive. Those 2 is going to cancel into 4, leaving a 2. So I'm going to get 6 minus 6. And so that's going to give me 0. So that tells me that over here at negative 4, I'm at 0. And that's going to be an open circle, because it is just less than. Now from that, you're welcome to use your slope. Keep in mind the slope is negative, and so whenever we do this, we might want to, instead of going, let's see, down 3, right 2, why don't we go up 3, 1, 2, 3, and then back 2. And that'll help us. And again, we can go up 1, 2, 3, and then back. And then that's going to give us the shape that we need for this. So I'm going to connect those, and that's going to be the linear side of it. All right, now we've got our absolute value function next. And we should know what that looks like. And we know that it's been turned over. So we know it's upside down. We also know that it is centered at 0, 0 because there's no transformations for it. So I'm going to go ahead and put that point there. Now I'm going to substitute in both of my endpoints so I know where this starts and stops. So if I substitute in that negative 4, I'm going to have negative absolute value of negative 4. So that's going to give me negative 4. So here I know at negative 4, I'm also at negative 4, so we're going to go over and then down 1, 2, 3, 4, and that's going to be a solid circle because it says or equal to. Now let's go plug in 1, and so I have negative absolute value of 1, so that's going to give me negative 1. So I'm going to go over to positive 1 and down 1, and that is also a closed circle. So now, since I know the vertex is at 0, 0, and again, I know that from my transformations, so there's going to be that part of the graph. Now let's move on to the last part. Again, we notice that we have a parent function, and it is a square root, and so we kind of know what that should look like. And we also know that we have been moved to the right 1 and up 3. So from 0, 0, we've gone to the right 1 and up 3. 1, 2, 3. And here, this is going to be a unique point because here, let's see, again, we're sitting right there from 0, 0, right 1, up 1, 2, 3. We're sitting right there. So let's go back and look. If I plug in that 1 over here, that's going to give me the square root of 1 minus 1 plus 3, 0 plus 3. So that's going to give me the point I just plotted. And notice it says it is open circle. So this part here has got to be an open circle. So let's go fix that. We have an open circle at, again, 1 and then up 3. We have our open circle. Now, again, that was our transformation. We can go ahead and maybe plug in another good value to the right that might help us plot another point. And it looks like maybe if we plug in maybe a 2, if we plug in 2, we're going to have the square root of 2 minus 1 plus 3. So that's the square root of 1 plus 3. Well, that's going to give us 4. So I know over here at 2, we're up 1, 2, 3, 4. And so that's kind of giving us an idea. Now we could continue on. If you wanted to even get more points, you could plug in a 5 minus 1 plus 3. So that's the square root of 4 plus 3. 2 plus 3 is 5. So you know over at 5, 2, 3, 4, 5. You're up 1, 2, 3, 4, 5. And so that should be enough to get your general shape, So again, you know you've got something like this. All right, now let's go answer some questions about it. Over here on the side, our domain. And the domain looks like every part is filled up, so our domain would be all real numbers. Our range, not so much though. Our range, it looks like the lowest this would go is -4. So we're going to have from -4 to infinity. And our types of discontinuity, it looks like we have two jump discontinuities. We're going to have one of them at x equals -4 and the other one at 1. And those are both jump discontinuities. Okay, for our next few problems, we are having to find our average rate of change. And keep in mind for your average rate of change, or AROC, that's going to be where we did f at b minus f at a all over b minus a. And keep in mind that was whenever we were over an interval from a to b. So in these examples that were given, we have our interval from -3 to 2. So we can go ahead and set up our denominator. We're going to have 2 minus a -3. That's the denominator. The numerator is going to be f at 2 minus f at -3. Okay, so now we need to do some number crunching here. And in that number crunching, we need to find f at 2. So over here to the side, and you're welcome to use a calculator as needed. F at 2, you're going to plug in a 2. So we're going to have 2 times 2 squared, which is 4, minus 3 times 2, and then plus 1. So f at 2 is going to be 8 minus 6 plus 1. So that looks like we're going to get 3. Now we need to find f at -3. And if we do that, again, we're going to have 2 times -3 all squared is 9. And then we have minus 3 times minus 3, so plus 9, then plus 1. So we're going to have 18 and 9 is going to be 27 and 1, so 28. And so now we're ready to come back over here and substitute in f at 2 we found to be 3 minus f at -3 was 28. And that's going to be over 2 minus a -3, so that's going to give me 5. So here it looks like we're going to get -25 over 5. So we're going to have -5 for our rate of change. All right, looking at 28, same process again. Given this a and b value, we already know that the denominator is going to be -5 minus a -10. Now over here to the side, we need to find f at -10, and we also need to find f at -5. The numerator is f at -5 minus f at -10. So f at -10 in the numerator, we're going to have -20, and then minus 1, so -21. In the denominator, we're going to have -10 plus 3, so -7. So that's going to give us a +3. All right, now let's plug in -5. So we're going to get -10 minus 1, so -11 over -5. And then plus 3, so that's going to be -2. So that's going to give us +11/2. All right, so now we're ready to go plug in. So in the numerator, we're going to have f at -5, so we're going to have 11/2 minus 3 over -5 minus a -10, so plus a positive, so over 5. And so when we subtract these, keep in mind you do need a common denominator, and if we change that 3, that's really going to be a 6 over 2. And so now we're going to get 5/2 over 5. And so keep in mind, keep change flip. So we're going to have 5/2 times 1 over 5. So all of that works out to be a half. For problem number 29, you have a football that is kicked from a point on the ground such that your height is given by this equation here. T is your time in seconds. Find the average rate of change, so that's going to be your A rock. And so your average rate of change formula again is going to be your function's value at the end of the time minus your function's value at the beginning of the time over the difference of the time. And so the average rate of change is going to be over the time frame from when the ball reaches its maximum height until it reaches the ground. So your maximum height here, to find that, you're going to, since you have a parabola, then that maximum height is going to be equal to negative b over 2a. And so that's going to give you, here this is going to be your b value, so negative 80 over 2 times negative 16. And so that's going to give you negative positive 2.5. Okay, now to find till it reaches the ground, then you're going to set the function equal to 0. So 0 equals negative 16. That should be x there, or that x squared should be t squared plus 80t. And this, you need to take out a GCF, which is probably going to be a negative 16 and t. And so you're going to have t minus 5. And so setting each part of that equal to 0 is going to solve your t value. And so at time t equals 0, well, that's the beginning. And then at t equals 5, that's the ending. So now you have your interval here. That interval is going to be from 2.5 to 5. That's going to give you the time frame that you're looking for. All right, so now let's go find our average rate of change from this. So you're going to need to find h at 5 minus h at 2.5 all over 5 minus 2.5. And so in the calculators, h at 5, and you're plugging into the original function h, that's going to give you 0. And then h at 2.5 is going to give you 100. So up here, your average rate of change is going to be 0 minus 100 over this difference, so that's going to give you 2.5. And so when you type that in the calculators, you're going to get a negative 40 and then feet per second. And keep in mind, it's okay that that average rate of change is negative, because again, you're going to have this parabolic shape. And so after it reaches this maximum value here at 2.5, notice that the height is now decreasing. So that's why your rate of change is negative. The next part of your review, you're going to look at a graph to determine whether or not you're symmetric about the x-axis, the y-axis, or the origin. So looking at this, it kind of looks like you might be symmetric to at least the x-axis, because we are a mirror image over that x-axis. And so to show that, then we plugged in a negative, over the x we would plug in a negative y. So let's go back. That's going to be x squared minus negative y all squared equals 4. And notice that I get back the original. And so here, that's going to tell me that we are symmetric about the x-axis. But this one also looks like it might be symmetric about the y, so we need to go check that. And if we're symmetric about the y, That means we're flipping over this way. So now we need to sub in a negative x to check that. And yeah, you get back the original. And so we are also symmetric about the y-axis. Now, looking at it a little bit more, it also looks like if we were to turn this 180 degrees, we would maintain that same exact graph. So this also looks like it might be symmetric about the origin. And very quickly, doing this substitution, you do see that you're also symmetric about the origin, because you do get back the original. So here you are symmetric about the x-axis, you were symmetric about the y-axis, and you were also symmetric about the origin. Okay, let's look at our next one. And this one looks like, just looking at it, it looks like we might be symmetric over the y-axis. So if we're going to check symmetry about the y-axis, then again, keep in mind you sub in a negative x. And so looking at this, we have the absolute value of negative 2x, then minus 5. And keep in mind that's going to generate the same exact value that this would. If we started plugging in numbers, notice you will get the same exact value. So this one would be symmetric about the y-axis. For our next part, we were talking about even, odd, or neither. So for that, even, odd, or neither, then we are going to look at whether or not what I get when I substitute in a negative x. Just a quick review of those rules. If we do sub in a negative x and we get back the original function, then we were even, and that was symmetric about the y-axis. If we sub in a negative x and that gives us back a negative, or the opposite of the original, then that tells me that this function is odd. But now be careful, it's not symmetric about the x, it is symmetrical about the origin. It could not be symmetric about the x-axis and maintain being a function. It would not pass the vertical line test. Alright, so looking at 32, we're told that this is a function, and so what we need to do is substitute in a negative x and compare it back to the original. That's always the first place to start. And if we sub in a negative x, notice that we do need to simplify, and this would turn into a positive 3x cubed and then a negative 5x. So notice if I compare this to the original, then notice that we have something completely different. So we know it is not even. So you need to now check negative 1 times f of x. So I'm going to say negative times negative 3x cubed plus 5x. When I distribute the negative, we're going to get positive 3x cubed minus 5x. Now you need to compare what we just got here. We need to compare that with what we have here. That's the test to see if you were odd. And notice that we did get back the same exact equation. So that tells me that this function is an odd function, and it also tells me then that we are symmetric about the origin. All right, let's look at the next equation. And we need to sub in again. You always start there with your negative x. So f at negative x That's going to give me 5 times negative x all squared plus 2 times negative x and then minus 1. So f at negative x is going to be 5x squared minus 2x minus 1. And so comparing that back to the original, those two are not the same. So we're not even. So now let's go back and look at a negative 1 times the original function. And so a negative times 5x squared plus 2x minus 1. And let's distribute. So we get negative 5x squared minus 2x plus 1. Now we compare that to right here, not the original, but to f at negative x. And notice those two are different. So this function would fall under the neither even nor odd. Okay, the next part we're looking at our function notations, and we need to talk about any kind of domain restrictions. And so the first part here, g plus f at x. Keep in mind that notation means g at x plus f at x. So we need to find function g at x, which is going to be the square root of x plus 7. And I need to add to that function g at x, or f at x, sorry, and that's going to be 3 minus 2x. So there's nothing much we can do with that. That's going to be our final answer. Now to check our domain, whatever's under the radical, that's what I'm going to move down here and say that has to stay greater than or equal to 0. So x has to stay greater than or equal to negative 7. And so there's our domain. Our domain is just going to be x is greater than or equal to negative 7. Okay, number 35, notice that function notation implies multiplication. So for this function, we're going to have to say h at x times f at x. And so h at x is going to be x squared minus 5x times f at x, which is going to be 3 minus 2x. Okay, for this, we're going to have to do our FOIL. So we're going to do our first terms. That's going to give me 3x squared. Our outer term, that's going to give me negative 2x cubed. The inner term, negative 15x. And then the last term, so that's positive 10x squared. And now you can combine your like terms. So we'll put those terms together. Let's see, this term needs to come first, so we have negative 2x cubed plus 13x squared, and then minus 15x. All right, now let's go look at any domain restrictions for this one, and this is a polynomial, so this domain is going to be all real numbers. Okay, number 36, we have a fraction here. Keep in mind that notation implies f at x over h at x. And so f at x is going to be 3 minus 2x over h at x, and h at x is x squared minus 5x. Now, don't try to cancel here. There's not an x in every single term, so this would be your final answer. However, you do need to check your domain restrictions, and you do have a denominator down there. So we're going to have to set that equal to 0. You can factor out an x, and then set each part equal to 0. So x is going to be equal to 0. And then x minus 5 is equal to 0, so x is 5. So here my domain is going to be all real numbers except 0 and 5. Our next set of problems is dealing with our composition functions. Do remember that the notation here, that's going to be our function h of f of x. So I'm taking the entire function f at x and I need to substitute that in over here at h at x. So that notation, we're going to have 3 times, and let's see, f at x is negative x squared minus 2x. So there's the first part, 3x, and then it's minus 1. We need to do our distributive property here, and then bring down negative 1. And that's about all we can do for that. As far as our domain, since this is a polynomial, it's going to be all real numbers. All right, so for our next one, the notation here again, f of g of x. So here that's implying that we substitute in. So we're going to take our function g at x, and I need to sub that in over here everywhere I see an x for f at x. And so I'm going to have negative, and then parentheses, the square root of x plus 7, all squared, minus 2 times the square root of x plus 7. And so we have negative times, and we're just going to get x plus 7 there, minus 2 times the square root of x plus 7. And that's about all we can do with this. You can distribute the negative if you need to. Now for our domain restrictions, again, what's under the radical has to stay greater than or equal to 0. And when we solve that, we're going to get our domain to be x has to be greater than or equal to negative 7. Okay, our next problem, we have the composition of f and h at x. So we need to take our function h at x and substitute that in to f of x. So we're going to have negative parentheses 3x minus 1 all squared, and then minus 2 times 3x minus 1. Now with that 2 there, do remember you need to FOIL that out. So let's go over here to the side. And so that's going to be 3x minus 1 times 3x minus 1. And remember, you have to do your first, outer, inner, and last. If we multiply our first terms here, we're going to get 9x squared. Multiply the outer term, and then the inner term, and then our last terms again. So when we put that together, we're going to have 9x squared minus 6x, and then plus 1. Now over on the other side, we do need to distribute with that negative 2. And so now we're ready to put together our like terms. And when we do that, then let's see what we're going to get. Here we're going to have our, I pulled that out. Now I need to bring down the negative. Oh no, guys, I forgot my negative. So that's going to be negative 9x squared, positive 6x, negative 1, then negative 6x, and then plus 2. Right, now these 6x's looks like they're going to cancel out. So I have negative 9x squared, a negative 1, and a positive 2, so positive 1. And again, this is a polynomial, so that tells me that my domain is all real numbers. Okay, so for our next two problems, what you're doing is working this backwards. In other words, you've got this, and that made up h at x. Now keep in mind that that notation means f of g of x is going to be h at x. And so what they're wanting you to do is try to figure out, well, which one was f of x and which part was g at x. So g at x would have been the part that was plugged in. So I would think right there, that could have been g at x. And then that would mean that f of x would have been 5 over x minus 2. And same idea over here, we need to find f at x, and we needed to find g at x, and g at x is what was plugged in. And so right here looks like an x plus 5 probably was plugged in, and then the original, you would just go back to that being an x. All right, so now we're going to be evaluating these composite functions. And so here are just regular functions. We need to find g at 15 minus f at 15. So g at 15, if we sub in a 15 right there, then we're going to get 30 minus 3, so I need the cube root of 27 minus, and if I plug in 15 here, that's going to be the absolute value of 10 minus 30, so negative 20. And so simplifying here, that's going to give me 3 minus 20, so we should end up with a negative 17. All right, for 43, keep in mind, again, that notation means h at negative 12 over g at negative 12. So h at negative 12, we're going to sub in here. And so that's going to give me 1/2 times negative 12 plus 5 over g at negative 12. So that's going to be the cube root of, and if I multiply those, that's going to give me 2 times negative 12, which is going to be negative 24, and then minus 3. And so simplifying, the numerator is going to be negative 6 plus 5. The denominator is going to be negative 3. So it looks like we're going to end up with a positive 1/3. And finally, number 44, we need to find g of h of negative 6. So first thing, find h at negative 6. And so we're going to have 1/2 times negative 6 plus 5. And so that's going to give me negative 3 plus 5, so positive 2. And so that means now we go back and we find g at positive 2. And so we're going to have the cube root. And if we plug in a 2, we're going to get 4 minus 3. So the cube root of 1 is just 1. And that would be your final answer. Okay, the next ones, we need to determine whether or not our functions are one-to-one, which means they have to, first, of course, you've got to pass the vertical line test, and then the second one would be the horizontal line test. So for this first one, if I draw a horizontal line anywhere, I'm only intersecting that graph once, and so the first one would be yes, you are a one-to-one function. Now, if I try that with 46, right away we see there's 2 places here, so that one would be a no. And the same is true for the next one. That one also would be a no. Okay, so for these problems, we're finding the inverse. And remember, this really meant y. And our first step, we need to swap x and y. And so we're going to have the cube root of y minus 7 and then plus 2. We're going to subtract the 2 over, and so we have now the cube root of y minus 7. We will then cube both sides, and so we have x minus 2 all cubed equals y minus 7, and then lastly we'll add our 7 over, and so we're going to have x minus 2 all cubed plus 7 equals this y, but that y is really the f inverse, so we're going to say equals f inverse of x. Now we need to look at a domain restriction, and here we have we're not doing a square root or we're not doing a fraction, so this would be the domain is all real numbers. Okay, our next example over here, notice that when we graph this, this would not pass the vertical line test, or I'm sorry, the horizontal line test. So this would be a skinny v. We have moved it to the left 5, and so this is going to look something like this. And if we do a horizontal line, this function is not one-to-one, so here we would have no inverse. All right, so now moving on to number 50. Again, now this one we're tempted to say no inverse, but let's look at what this is saying. We do have our U shape, and it has been moved down 7, and it's skinny, but this is only going to be for x values that are greater than 0. So whenever we're looking at this, we only have this side of our parabola. So then that would pass the horizontal line test, and we do have an inverse here. So let's go ahead and try to find it. And again, a quick reminder that your f of x has changed back over to y, and we do swap places with x and y. And so we're going to have x equals 4y squared minus 7. And so we have x plus 7 equals 4y squared. And now we're going to divide by 4 equals y squared. And now when we do the square root, we're used to saying plus or minus, but notice that we're not really going to have to worry about all of that simply because here we're keeping all of this positive. So we know those y values are going to be kept on the positive side of things. So here then I have the square root of x plus 7 all over 4, and then that's going to be equal to y, but y is going to be really f inverse of x. Our domain restriction on this, if we're looking at our inverse here, we would need to try to keep x to stay greater than or equal to -7 on that. And so if we look at the inverse of this, this would be flipped over and going over to our positive side of things. All right, looking at number 51, this one again would pass your horizontal line test. We do change f of x to y, and we're going to change places with x and y. So I have x equals y minus 6 over y plus 5. And now we're going to multiply both sides by y plus 5. And that's going to remove that from the denominator. And if we do that, then I have y plus 5 times x equals y minus 6. Now this time we are going to have to go through the distributive property because I need to get my y's together, and this is going to be the only way I can access that y that's inside the parentheses. And now I'm going to get my y's together on one side, and then I'm going to move that 5x over with the 6. Now you have a GCF right here, so I'm going to factor out a y, and x minus 1 is left equals negative 5x minus 6. And now we're going to divide both sides by x minus 1. And now we're left with our y, which we're going to say f inverse of x equals negative 5x minus 6 over x minus 1. And now we need to talk about the domain, which is going to be all real numbers except for when x is 1. And that's because if I set that denominator equal to 0 and solve, that's going to give me a 1 there. Okay, and for the last two problems, we are graphing a function and its inverse and proving that these are inverses of each other. And so the first way to prove here, I'm going to show f at g at x that has to be equal to x. So I'm going to take the entire function and I'm going to substitute into that denominator. And so that's going to give me 4 over x plus 2, and then I'm going to have a minus 2 out to the side. And keep in mind the whole idea keep, change, flip. So we're going to keep our first part, and we can think of that as over 1 times x plus 2 all over 4, and then minus 2 out here. Our 4's do cancel, and so I'm left with x minus 2, or I'm sorry, x plus 2 and then minus 2, and then those cancel, so I am left with just x. Okay, now if we show the other direction again, that other direction, that would be g of f at x. So we're going to change the directions here. I'm going to say 4 over, and then instead of x, I'm going to put 4 over x minus 2, and then there's also the plus 2 in the denominator. Again, those are going to cancel, so I have 4 over x, and again, we can do our keep, change, and then flip, and notice we are left with just x. So we've proven that these are inverses of each other. We got x here and x here. Now, for the next part, it does ask us to show this graphically, and so when we graph this, you may use your graphing calculator, or you may use your parent function transformations. Either one you want to do is fine. For this, I would go ahead and try to use some parent functions to make the process a little bit quicker. Do keep in mind you do have some asymptotes here. You've got the first asymptote that you can look at is going to be sitting at 0. So here again, this asymptote would still exist sitting there. And then you also have the other one where you've moved down to. So we've got this that we can look at. And so you also have an asymptote here. So those are just from your parent functions looking at it, or you can go through and find those on the graphing calculator, either way. And so for one of the zeros that we could find, keep in mind we could let f of x be 0 on that first function, and we have 4 over x minus 2. So solving this and then swapping places with your 2 and your x, so x is 2. So I know at 2, 0, there's one of your points where you're going to cross over. And so here we can do a rough sketch. Again, it doesn't have to be perfect, but a good rough sketch of that first function there, and then also here. Now, if we're going to look at our next function, that one's been moved over to negative 2. It's been moved over here is that asymptote. And then we also have at 0 for that one. And by that same process, we could go through and find where we would intersect over on the other axis, or we can just go ahead and do a good sketch of it from based on what we know. And so here, this one, it looks like would probably be bent as it heads toward that direction. And then up here, same idea. Okay, and so there's a good idea of what those should look like, and we can just see where we are reflected over the line, y equals x, well, or close to it, and we're going to see that those do reflect over that line. And number 53, just like 52, our first thing we need to show is that these are inverses of each other. So we do need to find f of g at x. And when we do that, we are going to hopefully get x here, and so we are going to substitute in. So I have 1/2 x, but in place of x, I'm putting 2 times the cube root of x plus 3. That is all cubed minus 3. Our 1/2 and 2 will cancel, and then I'm left with the cube root of x plus 3, all cubed, and then minus 3. And so that's going to leave me with x plus 3 minus 3, so we do end up with x there. Okay, so over on the other side of things, we need to do g of f at x, and so we're going to plug in and hopefully get x on that side there. So if we do that, let's go look. We're going to have 2 times the cube root of, and in place of x, I'm going to put 1/2 x all cubed minus 3. Now that was the entire f of x function, and then plus 3. So those are going to cancel each other out, those 3's. And so I have 2 times the cube root of 1/2 x all cubed. And do keep in mind your order of operations. The parentheses in that cube root are going to cancel each other first. So that's going to be 2 times 1/2 x. And once again, we do end up with x. So we have shown that they are inverses of each other. And again, when you graph these, do keep in mind your parent functions and how they should be reflected over that line y equals x. Important for us to realize that they are mirror images of each other over that line. All right, and so again, our parent functions here, we have our cubic function, and it's been moved down 3, and it does have the transformation there. So for this one, keep in mind that it should look something roughly like that, and then you're going to come across the other one that's going to be flipped over, and it's going to do something like that. And again, y'all can use your graphing calculators to help you with those.